must make some decisions and will suffer losses that are potentially adversarially determined. And so traditionally in online learning, you care about like a single string of losses, but we'll be considering a multi-objective setting where we want to not suffer too much regret with respect to a whole bunch of objectives. And the word minimax here refers to the nature of this framework being game theoretic. That's how we'll derive it. But I would like to begin this talk by going over a couple applications first. So I'll first quickly recap the mention of multicalibration. It's a recent and very exciting development in the field of pyramids with lots of cryptographic and computation implications. Then I'll talk about multicalibrating, sort of recent offspring of that notion, which basically says, try to get more calibrated and actually derive some accuracy benefits off of that. And then I'll quickly talk about sort of like multi-group roulette flavored notions. So all of these and more applications can be derived from the framework that I'll talk about at the very end of the talk. So calibration, vanilla online calibration basically says we'll have a sequence of rounds, and on each round, let's predict sort of from a discretized grid of predictions, and then we actually get to see the realized label. And calibration means, roughly speaking, that for any of the possible discretized predictions that we would make over the subsequence of rounds when we actually make that prediction, the true realized labels are actually close to that prediction in this average absolute value sense. And this notion appears to be useful, and you can in fact get it sort of for free, right? So you don't actually have to have knowledge of the data and the labels to achieve this. So this is a standard result by Foster and Vora. But calibration has some problems from, in particular, a fairness standpoint. So basically, we can imagine that we are making hiring decisions, let's say, and we hire or don't hire. And suppose, I receive applications from, a population that's split roughly half and half into two subpopulations. And for some reason, the first subpopulation, everyone's qualified, and the second subpopulation, no one's qualified, right? And then I'll do the following simple thing. I'll just always flip a coin, and the probability is 1/2 I'll hire, the probability is 1/2 I won't. Well, this is a calibrated prediction strategy because we always predict the same thing. And indeed, while we're predicting it, sort of the average candidate does have this 1/2 qualification because half of them are qualified, half of them are not. But one could argue that this is not exactly fair towards those people who are in the very qualified subpopulation because we're hiring them at the same rate as those people who are not qualified from the subpopulation. And so we want to ameliorate that by actually enforcing calibration on each subpopulation. And this solution concept is called multicalibration. I'm very honored to see some people who did sort of the original work and to introduce the concept. Basically, we receive, before the whole thing begins, as input, sort of a description of a collection of demographic groups. And then what we want to do is we want to make sure that our predictions are calibrated not just overall, but they're also calibrated when restricted to each subsequence of rounds that corresponds to people from a certain demographic group appearing. And you might be able to do this somehow if all these subpopulations are like non-overlapping, for example, but you cannot really do it in a simple way if there are all sorts of like intersections. So people can belong to some like arbitrary subset of this entire group family. And also the group family would like to potentially be very large, you know, maybe even on the order of how many like subsets of the entire population space there are. And basically multi-calibration in the online setting will sort of naturally fall out of the framework that I'll talk about. Calibeating is a recent twist on the notion of online calibration, and basically says, suppose each day we receive advice from a bunch of forecasters that belong to some family F, and each forecaster is like an expert, basically makes a prediction. Let's suppose it's also discretized like this for simplicity. And let's measure each forecaster's success by, you know, summing their squared deviations from the actual true label over all the rounds. So in all of our settings, we have basically some large but fixed time horizon, big T. Imagine that. So this is the squared loss, or also known as the Breyer scoring rule. And it has the following decomposition of the sort of bias, variance, and composition flavor. Basically, it can be decomposed into a component called calibration loss. And we can see that this is basically like an L2 version of the calibration constraints, right? So we're going to be summing sort of like the squared deviations of, you know, the average label predicted when we predicted like a certain, you know, discretized point algorithm. And the refinement loss is sort of the total variance within all the calibration buckets. So for each prediction that we could make, you know, it basically forms, you know, the sequence of rounds. We can make that prediction, and there's a certain variance that the realized labels have over that prediction. Okay, and so let's consider the following thought experiment, which was introduced by Hardy Foster. Suppose we could somehow real-time transform each forecaster's predictions such that that particular forecaster's calibration loss was like almost entirely gone, but the refinement component, you know, did not go up significantly, right? So that would mean it would basically like canceled out the miscalibration part, but we maintain the refinement part, so the squared loss would go down by the same amount of miscalibration that we fixed. And our goal will be quite ambitious. We want to make our own predictions, having observed these forecasters' predictions, so that our resulting squared loss would be basically as good as the best, you know, forecaster if we could transform all of them in this way. And a priori, it's not even clear that we can do this for like one forecaster that requires some thought, and let alone multiple forecasters. So Hart and Foster showed how this can be done. So calibrating these forecasters and the miscalibration amount there would sort of be, you know, polynomial in the number of forecasters. And with this framework that I'll describe, we can actually do better than that. And we can also calibrate them, let's say, on all groups and some collection of population groups. Yep.
Sure. Can you go over again what transform forecasters?
Right. So basically, like each round I receive this forecaster's predictions, and somehow maybe I even have like hindsight knowledge of what this forecaster like did all the rounds. And somehow I managed to like transform this forecaster in some particular way that the calibration component was.
The post-processing would want to what?
Yeah, to make it calibrated, but the refinement loss will sort of almost stay where it is, and calibration like claims that you can basically do that, you know, even when you have like, multiple forecasters to beat, even without sort of like this like hindsight knowledge. Yep. So this is another application that can easily fall out of the framework. And also here's a a slightly easier one. So basically, there are people coming, and there are like various judges that will pass their judgments on these people, and we want to sort of assign these people to the different judges so that if these people want different population groups, no group gets to experience like the hardest and most strict judge ever, whereas some other group gets easy verdicts that they're happy about. So we want to ensure that there is some sort of fairness there. So basically, we'll formally say these individuals are in a sequence and they belong to some groups, and we need to assign them on the fly to these like finitely many judges, each of which is prepared already to like make their decision y hat tj on this case. And different judges decide differently, so they might actually end up having sort of different error rates on different groups. So each judge makes their decision like no matter whether the person was actually assigned to that judge or not, let's say, for simplicity, right? And what we want to do is for each population group, we want to make sure that in hindsight, that group got almost as small an error as sort of the error of the best judge in terms of the like minimum error that could be assigned to that particular group. Okay, so basically this setting is a fun way of phrasing sort of multi-group regret.
So here, do you assume these y hat tj's for each judge? Okay, so you're assuming for each person that comes in, the outcomes of each judge before assigning them?
No, I first assign the person, then the judgment.
So only for the judge you assign the person to, do you see the outcome?
I see the outcome. No, so this is not like a banded setting. This is a full information setting. I get to see, like all these counterfactual judgments as well, basically.
Okay.
Hence why I have access to this benchmark. Okay, and other problems also fall out of this setting. No external regret, no internal regret, no adaptive regret, no phi regret, no many kinds of regrets. Calibration problems, including online multicalibration and other notions that we've developed alongside that, such as prediction error, multiplicity, a fast notion of Blackwell approachability that I won't have time to cover today, unfortunately, and other things. Okay, so this framework we will call online Minimax Multiobjective optimization. That's not the name for framework. But basically, so we imagine this generalized online setting where the adversary each round basically designs a game that they'll play in, and basically the adversary says, okay, I'll have this action set, and they have this action set, and I'm giving you like an entire vector of sort of like objectives, which I'll call LT, and like LTI is the I components in that last vector. Each component will be convex concave, so convex in my action, I'm the learner. I want to sort of like minimize the losses, and concave in the adversary's action, and continuous. And then we select an action, and observing our action, the adversary responds. So that's sort of like a second moving image. And we suffer like entire loss vector. And what our objective will be, it will be to minimize sort of the maximum coordinates of the cumulative loss vectors, loss vector over like the entire sequence of rounds 1 through t. So this is like a single dimensional objective that basically says the maximum loss over all coordinates should be as small as possible. Okay. And what we'll do now is we'll say, okay, how about we solve this problem using like zero-sum games. So just to recall, a zero-sum game basically has a max player, a min player, and Science Minimax theorem says that for convex concave utility functions, the order of play doesn't matter. So we might now say, how about we consider this utility function at each round, right? The maximum overall coordinates of what I can incur, right? And I can try to solve the zero-sum game. Unfortunately, this is impossible because this testing max over the coordinates actually deprives the adversary of the concavity. So what could happen is basically, if we were to go first, we could obtain a good payoff, but if the adversary went first, the adversary could obtain like a very high payoff. So that could be troublesome. Okay, so this doesn't work. So we have to be more sophisticated. Our benchmarks will basically say, okay, in this round T, if we could move first, we'll do the min, then the adversary does the max, presumably, and then the max row coordinates. So that's what we would achieve if we go first. But the adversary moves first value is actually what happens if the adversary moves first. That's more advantageous to us. We first get to see in this counterfactual world what the adversary did, and then obviously we could best respond and do well. But in reality, of course, we move first. But we still want diminishing regrets in this sense, right? So that's the maximum sort of like average loss coordinates at the end of history. And this is sort of like the sum of these adversary moves first values that would sort of happen to us if we could go first in each round. And we want this to be true. So that's sort of the AMF regret notion, okay? And basically what we do is we define a surrogate loss function because our previous actual loss function is not convex concave, so we can't do much of it. And what we'll do is we'll define sort of like a soft max of all these little constraints, right, relative to the adversary move first value. And then we'll just say, okay, let's apply some easy Taylor expansion, or the inequality really e to the x is at most 1 plus x squared, so nothing too hard. And basically, we define this surrogate game that basically says, okay, each surrogate loss is at most factor times the previous surrogate loss plus this, so we want to minimize this. And we'll actually solve this as a convex concave zero-sum game, okay? And we can actually here flip the order and imagine that we go first, the adversary goes first. We do not go first, the adversary does. And then we can actually obtain that this will be zero, right? By definition of the adversary moves first value. So basically this trick guarantees to us this regret bound, and essentially the things to note are that it's 1 over t as standard non-linear setting, and it has a logarithmic dependence on the number of loss coordinates. Okay, so instantiating this framework is very easy. And in particular in this multi-group, judge problem, we can basically define these intuitive loss functions and observe that if we could actually see the judge's judgments before each round, we could, optimally place each candidate with respect to, the best judge possible for that group, right? We just assign our current candidate to the judge who made sort of like the least amount of error in this round if we knew who that judge was, okay? And what is the algorithm? Well, the algorithm is basically, in this case, the exponential weights. In fact, our framework always sort of gives, spits out this exponential weight type of strategy. So assigned to the judge proportional to sort of the exponential of the previous like combined errors of that judge, okay? And multicalibration can be solved also in an easy way. So basically define each loss coordinate to be like plus minus the deviation of our current predicted label from the actual label, okay? And if you take the max over all such loss coordinates, you actually exactly get the definition of like calibration in the absolute value sense that I described earlier. In our earlier paper, I actually showed that like this algorithm exists. What it actually does is it basically approximately up to like 1/2 factor or something, which doesn't matter. Solves sort of the min-max equilibrium of this instantiation of our framework for the calibration case. And for multi-calibrating, we use a simple idea that's similar to the batch setting way of their original multi-calibration setting. We'll basically multi-calibrate our predictions with respect to all intersections of like each population group and each of our forecasters level sets, which in this case are basically the rounds when each forecaster like predicts like I over M for I between 0 and M, okay? And here, because our group has, our bound has logarithmic dependence on the number of coordinates, and coordinates correspond to these intersections, then we basically get a logarithmic dependence on the number of groups, as well as on the number of forecasters, whereas Foster and Hart in the original paper got a polynomial dependence in this case. And as I mentioned, lots of other problems can be solved in this manner. What matters is that we long-term average satisfy some convexity, for example, linear constraints. And with that, I would like to thank you for your attention.